So the bottom line, again, every function you can write like that. And maybe let's carry that with us for the next. Oh, it's the previous one. Okay. And one, I mean, when you look at this, you kind of say, well, if epsilon bias sets fool this, then why doesn't they fool everything? Like, I mean, because every function is a combination of those. So how doesn't epsilon bias sets is like the ultimate PRG, besides the fact that there is no ultimate PRG? But why isn't like the problem solved and we are done? So can you see why?
Why is there no ultimate PRG?
That's later. There are too many functions to fool. Well, I don't know what an ultimate PRG is, but there is no one PRG that fools all functions. That's what I mean. Because there are too many functions. You can always invert your PRG if you have enough power. But never mind. Right, there is a big sum here. You see, it's like maybe you can fool each of those, but it's not like you fool everything in the wall. So let's see. So let's ask ourselves, exactly this question: to what extent does an epsilon bias set fools a function, any function? It's not going to be, typically it's not going to be good, but at least we can ask and answer the question, and sometimes it is good. For decision trees, for example, it will be good. So let's see. So what do I want to do? I want to just take any function. It's not going to be a linear function in general, any function, feed it with an epsilon bias set. Okay, so that's an epsilon bias set. And I should compare it against, right? The the output of the function, the expectation corresponding to the uniform distribution. And I want to bound this value, right? Whatever epsilon I'm going to get here, it's not epsilon, it's not that epsilon. Maybe I should call it an epsilon zero bias set, okay? It's not epsilon. I mean, I want epsilon to be the error. So I'm taking an epsilon zero bias set, and I'm asking what is the error as a PRG, how good is it a PRG for this function? So what should I do when I look at this function now? I mean, I plugged in an epsilon bias set to its input, and generally, who knows how it behaves? But what can I do in order to understand how it behaves?
Decompose it to Fourier basis.
Exactly. So I'm just going to decompose it because in terms of the basis elements, I know how it behaves, right? So what I'm saying is that this thing, let's just write that for a second. That's the expectation of, well, this is expectation over S. Maybe I should, I guess it's clear. You're going to sum over all alphas, F hat alpha, chi alpha of S. Right? Instead of writing F applied to S, I'm writing F applied to S, but decomposing it according to the Fourier basis, right? So this is F out of alpha, and this is chi alpha, and I'm feeding S to it. And whenever you have expectation and sum, or sum and sum, or expectation, you switch them. And if you have constants, you take them out. Right, I actually did nothing here because by linearity of expectation, or because sum are sums, and okay, what do I know about this thing?
Bounded.
Bounded unless?
Zero.
Alpha is
Yeah.
zero.
Exactly. So there are two cases, like the general case in which alpha is not zero and the other case. So when alpha is not zero, I'm going to be happy. Let me just write it for a second. And when alpha is zero, what do I get? I get F hat of zero, they're all 1 zeros. And this is 1, right? I mean, when alpha is zero, this is the constant 1 function. And what is this thing?
the average?
Exactly. It's the same as that. Right? They're equal. That's what we said before. So that's great. It means that when I actually kind of started to develop this orange part, I actually got that part inside. So this thing that I'm trying to bound, so this means that, let's call this star. So this means the star is precisely the absolute value of, I'm going over all non-zero alphas. Happens to be what I want to do because I know how to bound those. Right? That's precisely the case. Because the one sum in here, when you decompose it to the Fourier basis that corresponds to the zero alpha is exactly the thing I'm subtracting. And now using the, triangle inequality, I can write it like that. That's at most 1. The whole point. That's at most epsilon 0. Right? That's the point of fooling these functions. That's it. That's your answer. So every function is fooled by an epsilon 0 bias set, but the epsilon that it is fooled is it's not epsilon 0. It has this blow up by this quantity that kind of captures how large f is with respect to linear functions. Right? This thing. How would you call it, by the way, this quantity? I mean, if you had to invent a name for it.
Almost the one norm.
Exactly. So it's the L1 norm, and it is a norm, by the way. People throw in also, what they do is kind of, maybe I should be more precise. I mean, okay, we got rid of this alpha non-zero, but at this point, I don't mind paying it as well. It's just a small number. It's most 1. So, being generous and putting back the average of f multiplied by epsilon 0 to the bound, this thing is called the L1 norm or the Fourier L1 norm of f. Some people even just write L1 of f, like saying I don't care about the L1 of f, I care about only the Fourier bound anyhow. So why even putting the little hat here? But let's not go there. Let's just call it the L1 of the Fourier. Usually it's huge, by the way. Usually it's like, 2 to the n over 2 or something. It's you have many summands. Typically there will be like, you need to do this calculation, but there will be like 2 to the minus n over 2, and you have 2 to the n of them. This would be a huge number in general, but not always. So for some classes of functions, this quantity is small. And when that happens, you have a PRG, right? The epsilon bias set, as is a PRG.
Can you say that again? For most functions, do you mean for most Boolean functions, or are you?
Yes, right. So typically, for a typical, exactly. So for a typical function from 0, 1 to the n to 0, 1, L1 of f hat is like something like 2 to the n over 2. It's huge. And therefore, if you want to get this to be like smaller than 1, the least, right? You want this to be some epsilon. Then epsilon 0 has to be exponential in n, and a small bias set with an exponential in n error is of exponential size. So it doesn't work. And actually, it's kind of really precise. There is a 1 over epsilon 0 squared dependence, and that squared is exactly accounts for this too. But never mind. The point is that most functions are not fooled by epsilon by f sets just because the L1 norm of the functions, Boolean functions, is for a random function is huge. But some functions are small norm. For example, epsilon by set, linear functions. What's the L1 norm of a linear function?
1.
1, right? It's just a basis function. So it's 1 times the basis function, and the L1 is just this sum is just a 1 and many zeros. It is 1 exactly when you are that function and 0 otherwise. Anyway, that's not very promising, but just saying. So, and what we are going to prove now, let's call it a theorem, even though it's like not that big of a deal, is that the the L1 norm of a function, which we said is a quantity which is important for us if you want to use epsilon bias set as PRGs, is at most the size, I don't know how to call it, dt size of f, I don't know. So the L1 norm, which is, you can think of it as some kind of complexity measure about f, right? The larger it is, well, definitely it will be harder to fool, but it actually means that it's, in a sense, kind of more random. So when this function is large, you're not really happy, but what I'm saying is that this complexity measure is bounded by that complexity measure. And that complexity measure is just the size of the smallest decision tree computing F. Number of leaves in the most economical decision tree computing F in terms of number of leaves. Okay, it's kind of cool. And it will immediately, as a corollary, we'll prove this, but as a corollary, any epsilon biased set, epsilon 0 biased set, epsilon 0 times, let's call it just dt of f, times dt of f fools, f. So in particular, it means that, if you take the other point of view, if you say, give me a PRG that fools all size m decision trees, some size m decision trees, so we have a PRG, it's really any epsilon by set, of C length log epsilon that fools the class of size m decision trees. Right, so I'll do the calculation in a second, but I'm saying that if you take an epsilon 0 bias set, that's the epsilon that you will end up with. That's the error that you will end up with given this theorem. And if we are considering only functions that are computable by size m decision trees for some parameter, instead of like looking at the dependency on the function, I'm just looking only on function with decision tree complexity m, then this means that an epsilon bias set, this is a proof of the corollary of corollary. It's very easy, just calculation. An epsilon bias set has this seed length, maybe a 2 here, plus a constant or something, but definitely O of log n over epsilon 0 seed length, right? Because the size is n over epsilon squared. Taking the log, you get something like that. There is a constant hidden in the size multiplicatively, so it translates to an additive constant when you take the log. But I don't mind. I'm just going to consider it as an O of log n over epsilon 0. But if you want to shoot for arrow epsilon, then you need epsilon 0 to be epsilon 0 over m, epsilon over m, right? Because as you can see, the arrow multiplies by m, right? So epsilon, the final arrow, is at most epsilon 0 times m. So, when you take the epsilon bias set against functions computable by size m decision trees, you prepare yourself and you take epsilon 0 to be, so what we'll do is we'll take epsilon 0 to be epsilon over m to make sure that the final arrow is most epsilon. And then when you plug it here, you'll see that you'll get seed length, which is log n m over epsilon, right? Because this epsilon 0 becomes epsilon over m, and the m goes up. Okay, I mean, aside from that theorem, is it clear that we are just constructed epsilon PRGs for decision tree of bounded size? Okay. So all we need to prove is that this theorem. So I want to prove that L1 of f is bounded by the decision tree complexity of f. Or in other words, if you give me, I mean, it's the same thing. If you give me a decision tree, a function computable by a decision tree with m leaves, then its Fourier L1 norm is at most m. Right? So proof of theorem. So, you're giving me this decision tree. Oh, you're giving me this decision tree. It has size m. So, m leaves. And I want to argue that the L1 norm of this function is at most m. Right? That would be enough. It's kind of the same thing, but I'm just calling this m. And looking at the decision tree. Also note, by the way, I don't need to know the decision tree. Just in the analysis, if you give me a function and you're able to prove a bound on its square complexity and the decision tree, then you're fine. It's only in the analysis that you look at the tree. So, do you have any idea how should I do that? I'll give you a hint. The only function for which we computed the Fourier spectrum is end of two variables, but it's kind of the same. So how can you express this in terms of ends? More or less. Right, so maybe this is x1, maybe this is x1, and you have a 1 here, and this is x2, and you have a 1 here and a 0 here, and maybe you have a 0 here. And here you have some value 0 or 1, here you have 0 1, and so here. So look at this path. I mean, what do you need to do in order to figure out if you reached here?
You end x1 and x2.
Exactly. So I should output this exactly when the end of x1 and x2 is 1. And I should output this exactly when the end of x1 and x2 not, right? Good. Is 1. And I should output this exactly when, x1 not is 1. So really, a decision tree is just m, the number of leaves, ends. And you can just add them like over the integers because they cannot appear simultaneously, right? If this end happens, this end don't happen, right? You only reach one of them. So what I'm saying is that you can write f, if f is this function, you can write it as a sum where for each leaf, if anything leaves, for each leaf, you have essentially an end. It's not really an end, it's an end of the variables and its negations, possibly, because you have zeros also. And the identity of the things you're taking end over depends on the leaf, right? It depends on the path. So I don't know how to write it like in a non-scary way, but it's something like, the index depends on the leaf that you're looking at, the path, but it doesn't really matter. Also, the number, by the way, that's even worse. Like the number of things you're looking depends on the leaf. And also there are like negations that I'm kind of hiding in between, right? Maybe. But do you understand? Do you agree that with some proper notation, also introducing these negations, really this function, this is the sum over the reals, okay? These are 0, 1 output functions, but this is the sum over the reals. It's fine, right? I mean, we are looking at functions to the reals, but really it's also a 0, 1 function because two ends are never 1 simultaneously here, because the ends mean I arrived to this leaf, and I couldn't have arrived to two different leaves at the same time, like under the same input. It's really just a partition, right, of 0, 1 to the end, to each square. And the part is determined by a certain end. Good, so do we agree that this holds? Do we not agree that this? I mean, silence is good, right? Usually,
In a decision tree, in the leaves, you need to return 0 or 1, right? Or
right. So only you're right. Only accepting leaves. Sorry, you're right, Itai. So I'm going only on the leaves that I accept. You're right. Yes, even less leaves. So I'm only looking at paths leading to an accepting leaves, and I'm adding the ends to those paths. Right. So therefore, if the input actually arrives to an accepting leaf, the corresponding end will light up. It will be 1. The others will be 0, and you'll get a 1.
so you actually fool
Right.
larger trees, but with
Few
only
accepting.
accepting leaves.
Yes, right. Yes. It's actually the size you can take to be the number of accepting leaves, right? But it's usually written like that, so let's keep with this notation. Good. So what can you tell me about the L1 norm of end? What do you think? I mean, what's your gut feeling? Maybe I'll go back to the example and you can see. So what happened with the end, right? So in the end of two variables, all the Fourier, I mean, it's not like a XOR. XOR has only, like a parity has exactly one Fourier coefficient, and all the kind of Fourier mass is concentrated on that Fourier coefficient, and it's 1. Here, the end actually is kind of disturbed over all Fourier coefficients, right? In this case, you have like all possible Fourier coefficients are non-zero, but all of them are 1 over 4. And so, at least for the two variable end, what is the L1 norm of end?
1.
1, right? I should add these in absolute value, right? And that will happen in general, right? Because this 1/4 is an artifact of the fact that only 1 out of 2 to the n things survived here, because end is usually 0. So in general, you will have all 2 to the n Fourier coefficients being non-zero, but all of them are plus minus 1 over 2 to the n. Right? So you will sum 2 to the n things, each of which is 1 over 2 to the n, because in absolute value it's 1 over 2 to the n, so it's 1. Okay, so you should convince yourself, but the end of variable is 1, and when you negate some of the variables, it's really an easy exercise. The only thing that happens is that some of the Fourier coefficients switch signs. They don't change in magnitude. So also the L1 norm of end with negations is 1. It's exactly 1. And therefore, what can I say about the L1 norm of F? I mean, it is a norm, the L1 norm. So sum and norms are good together.
It's the number of accepting.
Right. And so definitely it's at most M. It's actually bounded, as you said, and Itai said, the number of accepting leaves, but definitely at most M, the size. And we're happy, right? Because that's it. We bounded the L1 norm of F by M, which is the theorem statement, really. Questions?
I have a question about the bound that you said that typically it's very large.
This one.
Yes, it's just that. Well, isn't it like each coefficient when it calculated?
So good. So that's a standard deviation. So what really happens if you take a random function? That's a good question. Maybe I'll put it here so that when I'll put the notes. So if you have a random function and you look at f hat of alpha, and so what is f hat of alpha? It's the correlation between f and this -1 to the alpha x, chi alpha, when x is uniform, right? Just the definition. So this is the coefficient. It's the correlation between this thing. This is a 0, 1 thing, right? Between this thing and that. And the point is that if f is random, then you are doing like 2 to the n experiments here. You're choosing a number into 0, 1 to the n, and the average is 0. So every time this is either, so when f is 1, this is either -1 or +1. So you have like essentially 2 to the n experiments, maybe half of it, but 2 to the n experiments, and the expectation is 0. I mean, everything is like normalized properly. And so you would expect some standard deviation, right? You would expect that this won't be exactly 0 for random f, but rather you would expect it to be something like this thing, because there is some standard deviation, 1 over square root of the entire world. And when that's correct. And so that's typically what happens. And when you add the 2 to the n values of this magnitude, you get something like that.
For the alphas, the 2 to the n alphas.
Yeah, exactly. 2 to the n alphas. So you fixed f. So you fixed the random f. Like you're looking at a random f and you're adding overall alphas. Yes.
Yeah.
So most alphas will be like that. So when you sum them up, even there are some alphas that are not, it's going to be most of them. So you're going to get this bound. And plugging this, by the way, to an epsilon bias set is terrible, because epsilon 0 cannot eat this thing multiplicatively. I mean, it will require you to take epsilon 0 smaller than the 1 over that thing. And the effect on the seed length would mean that the seed length is at least n, which is good, because you need n random bits to fool an arbitrary function of n inputs. Because if you don't have any constraints on the function, you shouldn't be able to fool it. Okay, so I'll leave you with one question, and after the break, I'll answer it. I mean, usually when you do pseudo randomness, your day job is to put things in logs. Like you want to construct a pseudo random generators with seed length, which is logarithmic in things. That's what you want to do. So I'm asking, is this optimal? What do you think? I mean, I mean, I'm not asking you to prove anything, but do you feel like this is optimal? Namely, do you think there is a better PRG for size m decision trees with error epsilon, in n variables? Okay, so I'll go to the break now, and you'll try to think about that during the break.